Welcome back. This is part 2 of designing an acid-base extraction protocol. I know part 1 was longer than usual, but we accomplished so much in part 1. We were looking at using 2 different bases, and I think we have an idea now which one to use first, which one to use second. We also saw that maybe it's not great to use HCl to protonate these molecules because there would have been no way, at least I don't think there would have been a way to separate the two amines from each other very easily. With that knowledge in mind, we are going to make a flowchart, an extraction flowchart. And let me get situated here. This is part 2. I highly suggest that, after taking notes in part 1, maybe run through it one more time and just listen, okay, and see if those concepts are sinking in. But part 1 was number 04L50. Okay, and I have it right here with me. As a reminder, okay, we have these 3 molecules, and we want to do an acid-base extraction. The chloroform is actually more dense than water, okay, and we decided that it would not be a good idea to use sodium hydroxide first, because if we use sodium hydroxide first, not only will we get the carboxylic acid to go into the water, we would also get the less acidic phenol to go into water as well. Okay. The idea was to use sodium bicarbonate. Look what happens when we use sodium bicarbonate in a mixture of these 2 compounds. One of them will stay in the chloroform. The other one will go into the aqueous phase. Okay. Let me show you how I would design that flowchart. We have the 3 molecules, and actually, well, no. I was going to use abbreviations, but I think we do want to draw out the molecules to see the neutral form and the charged form. Okay. So all of them are in the neutral form, and they all are dissolved in chloroform. Let me just make sure I'm copying these structures correctly. Okay. We have our separatory funnel. And yes, we're going to put everything into chloroform, which I have as green. And yes, they are all soluble in chloroform. But what's the first thing I want to add? The next thing I want to add is I want to mix a base. And a base to deprotonate the stronger acid, but not the weaker acid. And as a reminder, it'd be cool to have the pKa's with us. The pKa for this carboxylic acid, we were using the Evans pKa table, is 4.2. Whereas this carboxylic acid, but the alcohol or the phenol, the pKa is 10.0. Okay. Which is the stronger acid? This is a stronger acid. So a weaker base should be able to deprotonate the stronger acid, but not the weaker acid. That is NaHCO3, the weaker base. And I'm going to use 10%. Now the actual percentage doesn't matter. We're still going to use the same pKa's. Okay. Remember, when we use this as the base, it becomes what? It becomes H2CO3, and that pKa from part 1 was 6.37. 6.37. Yes, so I'm not drawing out the reaction in a line, but think about it. You take this molecule plus this, and the weaker acid is here on the right-hand side of the equation, meaning that this is deprotonated. We have now a separatory funnel with the 2 layers, aqueous base and chloroform. The aqueous base, aqueous is less dense, okay? Chlorinated solvents are more dense than water. And what do we have? Because this can be deprotonated, right? Because equilibrium favors the weaker acid for this case in the aqueous phase, and it is sodium bicarbonate aqueous. We have this molecule in blue. In green, in the chloroform, the organic phase, what do we have? We definitely have this because this is not acidic. The acidity or the pKa of this is 36. That is not a strong enough base because look at the 2 pKa's, the one on the left and the one on the right. Equilibrium favors the left-hand side. This is the weaker acid. It's weaker than 6.37. But look at this molecule right here, 10 and 6.37. Which one is the weaker acid? This is the weaker acid. So this stays neutral. And that's the beauty of this first extraction, is that we only get one molecule into the aqueous phase because it's the only one that is charged. And we have these two still in the chloroform, NH2. Do you see that? All right, so the idea is to drain and then put back the chloroform into the separatory funnel. So there are 2 things that we need to do. We have, it's actually in practice, you would have to get a beaker, drain the green into the beaker, drain the blue into another beaker, and then pour back the green into the separatory funnel. So you have this. The green goes back into the separatory funnel. Okay. And what happened to the blue? The blue, after the green was drained, the blue got drained into a beaker. So the blue goes into a beaker. And what's in the blue phase? This molecule right here. This molecule right here. Now the thing is, it's soluble. This is aqueous. This is your NaHCO3 aqueous. So how do we collect this? It's soluble. Before we take care of these 2, okay, let me show you. We're going to do what's called a neutralization. And we're going to put HCl. HCl does what? HCl will actually make this not water soluble. Why? Because we're going to make it neutral. So when you have this beaker and you add HCl, sure, it's still water, okay, but now it's acidic water. What do we have? We have, let me use a different color. Let's use this blue. We have chunks now. Why did it fall out of solution? It fell out of solution because we reprotonated this. And what do we say at the very beginning? In part 1, when we were looking at these molecules? The neutral form is not water soluble. And it falls out of solution. Whether that water is acidic, okay, we should actually say that. Not water soluble, but specifically not HCl aqueous soluble. So that water is acidic because if it was basic, we would have this molecule. Then all you have to do is filter. Okay, and you've seen filtering before. We got this one out. This is a success. We were able to separate this molecule from the other 2. Where are the other 2? The other 2 are right here. Okay? Now, like from part one, if we use HCl, that would be bad because both of these will be protonated. So both of them will go into the water. So in part one, we concluded that this is not good because both will go in water. Both will be, and we could abbreviate it, NH3 plus, and go into the HCl aqueous layer. We didn't get a separation when we use HCl. And we can't get a separation if we use NaHCO3 because we tried. We used NaHCO3 in the first extraction and it did nothing to this molecule. Right, it stayed neutral because, again, this pKa, the one on the left, is a weaker acid than the resulting conjugate acid in that reaction. So it stayed like this. We have to use a stronger acid. So the second extraction, I know there's a lot going on here. I'll zoom out in just a bit. I'll try to get this on one-to-one page also. This is the first extraction. Let me put it in a box. Okay. To get this molecule. The second extraction is going to be with a stronger base, NaOH. NaOH, again aqueous, of course. And this is a second extraction. Remember, the only two molecules that are in the chloroform right now are these two molecules. It's in the chloroform. Okay. Well, let me zoom out a little bit to get the 6,000 foot view. Right? We're just chugging along, and now we have a new separatory funnel that has the two layers. We were able to separate those two molecules in between these two different layers, the blue and the, well, man, right there, between the blue and the green. Remember, this is, where do I want to write this? This is the NaOH aqueous on top. That's a strong enough base to deprotonate this molecule here. Again, what's happening here is that when you mix these two, this organic molecule and this NaOH, what is the result? The result is this molecule in blue O minus plus what? H2O. Remember, this H2O is the conjugate acid of the base. So the pKa's that you are comparing at the very beginning is the pK of this, which again is 10, and the pK of water, because that's the conjugate acid on the other side of the reaction. We said that was 15.7. Meaning that the right-hand side of the equation, the product side, is the dominant side, and you'll get this a lot. You'll have almost all of this convert into this, and this is water soluble. You notice in this molecule, there's no acidic functional group. This is actually considered basic, right? It has a pKa of minus 36. So it's very non-acidic. That stays in the organic layer. This is still the CH3Cl, and this molecule is neutral. There we go. All you have to do here now is when you drain, you're going to take this and evaporate the chloroform. So you'll separate this into a beaker, and you will have the chloroform evaporate. And when the chloroform evaporates, what will you be left with? you'll be left with a solid. There's no neutralization needed because it was never charged, and you have powder at the bottom. That is, again, I know we're drawing these molecules a lot, but that is this molecule here. Where's the dilemma? The dilemma is in this other beaker that has the aqueous phase. We have soluble this, right? It's soluble. What was the trick? The trick is to now convert it back into neutral. Just like over here, we had soluble benzoic acid in this beaker, and we protonated it to get back the solid, to get back the neutral form. The neutral form is not soluble in water, or specifically in this case, acidic water, and it starts to precipitate out. So really what we're doing is you're taking this molecule right here, and you are adding HCl. When you add HCl, what you'll notice in your beaker is that your water will maybe clarify, and then you'll get some precipitate. Because again, what is the idea? Uncharged molecules are not soluble in water, OH. And you go to filter again. Filter this solution. If we zoom out even more, there's our first molecule that we isolated. And then we were able to separate these two. This one was never charged, so there's no neutralization. We just have to evaporate the solvent. So there's that molecule. Now this molecule is charged, but I really want, right? I really want these three. I want all of them to be uncharged. So we add HCl, a strong acid that will reprotonate this oxygen, and we filter. Those are your three compounds circled in red, 1, 2, and 3. Not the most aesthetic flowchart, but we're just going down the center. I don't know if you could. We start here, right? We do our first extraction, our separation, put back the organic layer, and do a second extraction. Okay, separate the green and the blue. There's your green, and then we have to neutralize the blue solution with acid to get back this neutral form. Okay, that is the design, and that's how I would separate these three using acid-base extractions. Now, let's say you let this sit for a month or so, get more comfortable with organic chemistry. I bet you can think of other ways, other sequences of acidic water and basic water to try to separate these three. Okay, there's often several different ways to do that, to do an acid-base extraction, but we were able to do this pretty well with only 2 extractions, 1 and 2, and with our acid neutralizations. Whoops, here, this one right here, these two that I'm pointing at. Okay, I think that's all I want to say for now. Yeah, hopefully this helps. I decided to put this lab video with the other lecture videos, and hopefully this will help with your lecture class as well.